Let's get started. Good afternoon, everyone. I'm Ram Paudel, a researcher with NREL. Thanks for joining us this on-demand webinar, a part of the wind workforce development efforts here at NREL. Today, we are here with the second webinar of this series. Our presenters are Eric Simley and Henry Scholbrock, and the topic is Nacelle-Mounted LiDAR for wind energy applications. This webinar is being recorded. It should be available in NREL Learning channel in about 2 weeks. Educational tools and curricula to support university education are part of the NREL's wind workforce development effort. These NREL projects aim to enhance classroom activities at wind application center and universities. Our presenters are joining us today from an NREL Flatiron campus here in Boulder. I got opportunity to chat with Eric and Andy during a conference. Eric and Andy organized a joint workshop of IEA Wind Task 32 and Task 37 on the sidelines of NAWEA 2019 conference. Eric and Andy will take turns presenting different topics during this webinar today. I see remote sensing devices, especially LiDAR, has potential to make wind turbine and wind farm even smarter. I'm sure economy of scale and the technological improvements will bring cost further down. Cost may have already reduced significantly from when we deployed them first back when J4 was being tested at Renewable Energy Research Laboratory at UMass Amherst. One company was then working on a vindicator laser wind sensor for wind energy applications. There are various types of nacelle-mounted LiDARs, such as J4 DM. I'm sure presenters today will elaborate them.
We'll try to make this interactive series as possible. Please use the chat feature on Zoom so that you can submit your question to us. Please go to the chat and type your questions here. You will have an option of asking questions to everyone or a specific person. Please direct question to Liz Girls and she might merge them together. In any case, please keep your question coming. We'll have about 10 minutes for question and answer. With that, I'm going to hand it over to Eric Simley.
All right, thanks, Ram. All right, so I think we fixed the audio. We were muted for a little while at the beginning, but sounds like you can hear us now. Okay, so my name is Eric Simley, and Andy Scholbrock and I will be giving a tag team presentation here today. So I will start by just going over an overview of the talk. So first we'll introduce ourselves, and then part one of the presentation, we'll talk about the background or fundamentals of LiDAR measurement principles, going over the Doppler principle for measuring wind speeds with LiDARs, talk about the two main types of LiDARs, pulsed and continuous wave, and then talk about how LiDARs spatially average the wind in the probe volume when they measure the wind. And then the wind field reconstruction process, how we take the raw LiDAR measurements and determine useful wind field quantities from them. The second part of the talk will be about applications of nacelle-based LiDAR, specifically calibrating the yaw alignment of turbines, feed-forward blade pitch control using LiDAR measurements, and then power performance measurements, and a little bit about research applications using scanning nacelle LiDARs. All right, so again, I'm Eric Simley, a research engineer in control systems for wind energy here at NREL. And my experience with LiDAR started during my PhD at the University of Colorado Boulder in 2010, where I was optimizing the scan pattern of nacelle LiDARs for LiDAR-assisted control applications. Then in industry at Envision Energy, a wind turbine manufacturer, I worked on simulation and field validation of LiDAR-assisted controllers. And now at NREL, I'm mostly working on wind farm control and using nacelle LiDAR measurements to help with field experiments. Also wanted to mention that Andy and I are on the advisory board of IEA Wind Task 32, which is one of the many tasks under IEA Wind. Task 32 focuses on LiDAR for wind energy applications and is an international open platform for the exchange of experience in LiDAR for wind energy. So the task puts on workshops and meetings throughout the year and are a great resource for LiDARs for wind energy.
Okay, I'm Andy Scholbrock, and yeah, I've been at NREL since 2011, and during my time here at NREL, I've been working with LiDARs and integrating them into wind turbines from a controls background. So yeah, I've integrated several LiDARs into various wind turbine systems in the field for field testing, and then used the LiDARs for feedback and feed-forward control. And then also, the other area I've looked into is improved yaw control for wind turbines using LiDARs. So from that, we'll get started with part one, which is we're going to go over the principles of LiDAR measurement. So an introduction into the LiDAR itself. So LiDAR is an acronym which stands for light detection and ranging. And there's two types of LiDARs. The first is a range finding LiDAR. This is the type of LiDAR that you'll see in the automobile industry that are being used widely now for trying to automate vehicle driving. And so those are used to find the distance from the LiDAR to an object. And then the second type is Doppler LiDAR, and that's what this talk is going to focus on. The Doppler LiDAR uses, can measure distance, but also gathers information on the Doppler shift of the light that's being emitted from the LiDAR. And so it's similar to a radar, but uses a different frequency of light, which interacts with the atmosphere. And then from that, we can get information about the wind in the atmosphere. So the Doppler principle for measuring the line of sight wind speed, the Doppler effect is classically described with a moving vehicle and some sort of sound being emitted from that vehicle, and there's a change in pitch between when the vehicle is approaching versus when the vehicle is departing. So in the illustration here, we have an observer at position Y, and the vehicle is approaching that observer. And as the vehicle is approaching, the sound waves are being compressed. And so they hear a higher pitch frequency when compared to an observer at position X, where the vehicle is departing, and those sound waves are being expanded, and so the pitch is a lower frequency. And so the same is true for light, where an object approaching will have compressed light waves, and an object departing will have expanded light waves. And this has been used in astronomy in the past to determine whether distant stars are moving toward Earth or away from Earth. So going further into the principle of line of sight wind speed measurement, we have a LiDAR here on the upper left of the slide, and then in the upper right of the slide, we have a cloud here represented by a bunch of black dots. And the LiDAR is going to send out a beam of light into the atmosphere, and it's going to interact with those particles in the atmosphere. And in the LiDAR world, we refer to the particles as aerosols. And so then that light is reflected off of the aerosols and comes back, and we measure the shift in the light to determine where the aerosols are moving, and we assume that the aerosols are moving perfectly with the wind, and from that we can get a measure of the wind speed. So in this example here, we have compression of the wave, and from that we would then infer that the wind is moving towards the LiDAR. If the opposite happened, where there's an expansion of the wave, then we would assume that the particles are moving away from the LiDAR. And if we get the same frequency back, then we would assume that there's either no wind, or the wind could be coming perpendicular to where the LiDAR is measuring. So we can only measure along the line of sight of that beam of light. So if the wind's moving perpendicular to that, then we'll have no measurement. And so here's the basic equation that we use to gather the wind along the line of sight of the LiDAR beam. So we have the frequency shift of the light, and that's equal to 2 times the wind speed divided by the wavelength of the emitted light. So some other considerations when dealing with LiDARs is homodyne detection versus heterodyne detection. So most commercial wind LiDARs at present use homodyne detection to detect the Doppler shift. And what that means is that we only gather information on the magnitude of the Doppler shift, but we don't have information on the sign, whether it's a positive shift or a negative shift. And so from that, we don't know whether the wind is traveling towards the LiDAR or away from the LiDAR. With heterodyne detection, it is possible to gather both the magnitude and the sign of the Doppler shift, but it requires more hardware in the LiDAR, and it drives up the cost to produce that LiDAR. So other considerations with LiDARs is a carrier to noise ratio. So in other areas of electrical engineering, we have a signal to noise ratio. This is very similar with LiDARs, where we're measuring the amount of light we're sending out into the atmosphere versus the amount of light being reflected and coming back and measured by the LiDAR. And so if we have low aerosols, so a very clear atmosphere, then the CNR will be a low value. And it can get to the point where the atmosphere is clear enough that we're not able to measure the wind speed anymore. And another thing that comes up with, specifically with nacelle-mounted LiDARs, is blade blockage. So in the picture here, we have a LiDAR that's installed on a wind turbine looking forward, and we can see the blades here that are in rotation. And so there's going to be points where the LiDAR laser beams are being blocked by the blades when it passes in front of the LiDAR. So this is easily detected by the LiDAR because the CNR value will be very high because a lot of the light is being reflected back to the LiDAR. And so the LiDAR can see that it's an erroneous measurement because it's hitting a solid object. But with nacelle-mounted LiDAR, we've noticed from studies in the past that the rotor solidity is small enough that there's enough data captured between the blades passing so it doesn't impact our ability to measure the wind. And so then there's 2 types of LiDARs. There's pulse and continuous wave LiDARs. And these differ in how they capture the measurement of the wind. So a continuous wave LiDAR focuses the laser beam to measure a volume in the atmosphere around where that laser beam is focused. A pulsed LiDAR uses a coherent laser beam and sends that into the atmosphere, and then uses time of flight to measure a volume in the atmosphere. So basically, we know the speed of light, the laser beam is sent out, and then we wait a given amount of time, and then when it comes back, we know from the speed of light being constant where it came back from the atmosphere. So either of these LiDARs can be fixed beams or scanning. And yeah, so here's a table that kind of shows, compares the 2 LiDAR technologies. So we have the range measured, where for a continuous wave LiDAR, it's determined by the focus, and a pulse LiDAR is determined by the time of flight. The probe volume is constant for a pulse LiDAR, and it increases with the distance proportional to the distance squared for a continuous wave LiDAR. And then we have the minimum range is close for a continuous wave LiDAR and far, relatively speaking, for a pulse LiDAR. The maximum range for a continuous wave LiDAR depends on the optics, and for a pulse LiDAR, it depends on the laser pulse energy. And data processing for a continuous wave LiDAR is fast because it's happening on the fly as it's scanning around, whereas a pulse LiDAR is relatively slow because it needs to process many pulses in order to get enough signal back. For measuring multiple ranges, the pulse LiDAR has an advantage because it can measure multiple ranges from a single pulse and differentiate between the ranges based on time of flight, whereas a continuous wave LiDAR is slow and as it needs to refocus from one range to the next.
All right. Okay, thanks, Andy. So now we'll go into some detail about the LiDAR probe volume averaging that Andy mentioned, and we'll start with continuous wave LiDARs. So it'd be great if a LiDAR could measure the wind speed at a specific point in space, but due to physical limitations of the LiDAR, it's not able to focus the beam at a particular point. So we're going to measure the spatially averaged wind speed along the length of the LiDAR beam, weighted by what's called the range weighting function, determined by the physics of the LiDAR. So the range weighting function is shown here in blue, and it's highlighting how the wind velocities at our focus point are going to be weighted most heavily in the measurement, and then as we move away from the focus point, the contribution of those velocities will decrease. So the width of this weighting function depends on properties of the LiDAR, such as the telescope lens diameter, how tightly we can focus the beam. And then, as Andy mentioned, it's proportional to the square of our focus distance. So every time we double the focus distance, our spatial averaging increases by a factor of 4. So this figure illustrates what this spatial averaging looks like using simulated turbulent wind speeds, shown in blue, and then simulated CW LiDAR measurements in red for 5 different focus distances. So when we're focusing at a short distance, like 10 meters, there's very little volume averaging, and we're measuring very close to the actual wind speed. And then as we increase the focus distance, that probe volume becomes larger, and we start to measure the smooth wind speed signal. So it acts as a low-pass filter on the wind and starts to filter out the high frequencies. Up at 100 meters and 200 meters focus distance, then we're really just capturing the very slowly changing trends in the wind speed, filtering out all those high frequencies. So you might say that at 200 meters, that measurement is no longer very useful because we're not measuring very much of the turbulence. So for a pulsed LiDAR, it also spatially averages the wind when it measures the wind, but it's a little bit different than a CW LiDAR because now we're emitting a Gaussian-like pulse as it travels through different range gates. That will end up spatially averaging the wind speed. So the width of the pulsed LiDAR range weighting function depends primarily on the pulse width that's emitted from the LiDAR, and then on the spacing between range gates. So just a quick illustration of how a pulse LiDAR spatially averages the wind. So this is showing the pulse emitted by the LiDAR as it's traveling through the second range gate. So the pulse reaches range gate 2, which is 30 meters wide in this case. And so the LiDAR will start to integrate the backscattered light for this range gate. Now we're in the middle of the range gate, and finally the pulse is exiting that second range gate. So we'll stop integrating the backscattered light to form our measurement. So by combining this original pulse shape with the integration as it travels through the range gate, we end up with this slightly wider range weighting function, which is still very similar to a Gaussian function. And then just to wrap up volume averaging, this plot is showing range weighting functions for a CW LiDAR for 3 different focus distances, and the range weighting function for a pulsed LiDAR, shown as the dashed curve. And the pulsed LiDAR range weighting function does not depend on the measurement distance. It's the same pretty much every distance you're measuring. So for shorter focus distances, measurement distances like 50 meters, a CW LiDAR will have a smaller probe volume. And then for longer distances around greater than 150 meters, then a pulsed LiDAR will have a smaller volume averaging. But somewhere between 100 and 150 meters, CW and pulsed LiDARs tend to have about the same amount of volume averaging. Okay, the next topic will be wind field reconstruction. So this is looking at how we take those line of sight measurements from the LiDAR, line of sight velocities, and estimate useful wind field parameters from them. So this scenario that's illustrated here is just a simple 2-beam LiDAR measuring at hub height, measuring horizontally upstream of the turbine. So we'll define the direction the beams are pointing using the LiDAR direction vector. It consists of an X and Y component, where X is the direction aligned with the direction the turbine's pointing, and Y is that horizontal crosswind direction. So the line of sight velocity that we end up measuring with the beams is going to be the wind speed vector projected onto our LiDAR direction vector, where the wind speed vector has a U and V component, which correspond to the X and Y directions. But from our line of sight measurements, we'd really like to know what are these U and V components. That's what is more important for the turbine. So to do this, we have to make some assumptions. We have to use a wind field model. The first wind field model we could use is to assume that the turbine is perfectly aligned with the wind, so we have 0 relative wind direction, and our V crosswind component is 0. But we can have a horizontal wind shear, so different wind speeds on either side of the rotor. So in this case, from our line of sight velocity measurements without the V component, it's very simple to solve for the wind speed at our 2 measurement locations. And so we can get 2 different wind speeds at the 2 beam locations. Another wind field model, another assumption we can make is that we have a uniform wind speed, but with some wind direction. So now both LiDAR beams are measuring the same wind speed and direction, but from different angles. So our line of sight measurement will now be a function of the U and V components, where U is the horizontal wind speed times the cosine of the wind direction, and V is the horizontal wind speed multiplied by the sine of the wind direction. So there's a problem here, which is that we actually cannot distinguish between these 2 wind field models. We can't tell if we have horizontal shear or without wind direction, or if we have uniform wind speeds with wind direction, because there could be examples of these 2 types of wind fields that would produce the same line of sight velocities projected onto the beam directions. So this is what's sometimes called the Cyclops dilemma, where we only have one LiDAR or one eye, so we cannot see in 3D, and that means we have to combine our line of sight measurements with some assumptions, some model to estimate our wind field parameters. So going back to our measurements of wind direction, we can rewrite this as a matrix equation. So we have our vector of line of sight velocities equal to our U and V wind components multiplied by our measurement matrix. And since we have a nice square matrix, we can invert this and just solve directly for U and V. And then if we want to know the wind speed and direction, our wind speed will be the magnitude of the U and V components. And then we can also find the wind direction angle from U and V. All right, so now moving to 3D LiDAR scans, there could be a number of wind field parameters we're interested in measuring. Of course, just the hub height wind speed. And then we could try to measure horizontal shear or wind direction, as I mentioned. But we have to choose between these because of the Cyclops dilemma. We can't measure both at the same time with a single LiDAR. And then in the vertical direction, we could assume we have vertical shear or vertical inflow angle, which could be present in complex terrain, for example. So next, let's just look at a scenario where we're trying to measure the hub height, wind speed, horizontal shear, and vertical shear. And this scenario shows up sometimes in LiDAR-assisted control, blade pitch control scenarios where we want to know the shear for individual pitch control. So our wind field model consists of hub height, wind speed, and then horizontal and vertical shear. Those are defined as the slope of the shear, or the rate of change of the U component of the wind speed as a function of how far away from the hub we are in the Z and Y directions. And so the assumption we're making with this wind field model is that our crosswind V component and vertical W wind component are both 0. So now the line of sight velocity that's measured by a LiDAR beam is going to be a linear combination of the hub height, wind speed, and then the horizontal and vertical shear slopes. So we can, so let's assume we have a 3-beam LiDAR. So we have 3 measurements and 3 unknowns. So we can rewrite these line of sight velocity equations as a matrix equation where we now have our 3 line of sight velocities as a function of hub height, wind speed, horizontal and vertical shear, multiplied by our measurement matrix. So again, this is easy. We just invert that measurement matrix and can directly solve for our hub height, horizontal shear, and vertical shear terms. But what if we have a circularly scanning LiDAR that has 50 measurement points, or a pulsed LiDAR measuring at 10 different ranges? Well, now we have more measurements than unknowns, so we can't simply invert this matrix, but we can find the least squares best fit solution to this matrix equation. So just like we can find the best fit line in the scatter plot, here we're going to find the best fit wind field parameters to match our line of sight measurements. So to do that, we just take the measurement matrix and apply some matrix operations, and then come up with our least squares estimator matrix. So just to show what that might look like, say we have a complex wind field interacting with the turbine. We measure it at many different points with a LiDAR, and then we can fit that to a simple wind field model consisting of our hub height, wind speed, and linear horizontal and vertical shear.
Okay, so a summary of the part 1 of our presentation. First, we talked about the Doppler principle for measuring line of sight wind speeds, and LiDAR uses the Doppler shift off of reflected light from aerosols in the atmosphere to measure wind speed. Then we talked about the differences between the types of Doppler LiDAR technology, pulsed and continuous wave, and really the difference comes down to how they capture a volume in the atmosphere, pulsed using time of flight and continuous wave using focus.
All right, and related to that, we looked at how LiDARs measure the spatially averaged wind speed within the probe volume, and talked about how the range weighting functions for the pulsed and CW LiDARs are different. And then for wind field reconstruction, we saw how a single LiDAR does not provide enough information to reconstruct the full wind field, so we have to make some assumptions about the wind field and fit our line of sight measurements to a wind field model.
Okay, so with that, we'll go into part 2 now, talking about applications of nacelle-based LiDAR. So the first application is the yaw alignment calibration. So the problem here is that most commercial wind turbines have a wind vane that's located on the back of the nacelle, which you can see in the red circle here. So the problem is that the vane is measuring the wind only at one point in space where the vane is located. And for this setup, it's located just behind the rotor. So there's probably some error that's being introduced into the vane signal which is then being fed into the controller to determine which way to point the turbine into the wind. So what we'd like to do is measure ahead of the wind turbine in free space where the wind field is hopefully undisturbed. And then from that, we'd have a better idea of what the true wind direction is, and then be able to point our wind turbine into that wind direction. So here's some equations here that show the amount of power loss that can happen from a turbine that's misaligned. So the top equation here is the power that's available in the wind, which is dependent on the air density, the area of the wind turbine, and then the velocity of the wind speed that is going perpendicular into the rotor. So the perpendicular velocity is then dependent on the wind speed in the atmosphere and then the cosine of the yaw error. So the power loss is then approximately the cosine cubed of the yaw error. However, in practice, we have observed that the cubic value is more closely to a squared value versus the theoretical power loss. And then also when we're doing this with using a LiDAR, like Eric mentioned, when we're doing a reconstructing of the wind field, we need to make an assumption based on the measurements. And for this method, we're typically assuming that there's no shear in the wind, and we're just measuring the yaw error. So we did this on one of the wind turbines at NREL and put a LiDAR up on the nacelle and measured the wind, and from that determined that there was an error in our signal and then applied a correction to the yaw controller. So here we have results that show the baseline case where the wind direction is uncorrected, and that's in the black. And then in the red, we have a corrected value, which was, we then applied a correction to the yaw controller based on the error measured by the LiDAR. And the two plots here show, the plot on the left shows our wind direction as measured by the LiDAR, and the plot on the right shows the wind direction as measured by a nearby met mast. And we can see that using the LiDAR to correct the yaw controller, we had a nacelle yaw error that's much closer to 0. And from that, we also then gathered power data from the wind turbine and showed that the annual energy production was estimated to be increased by 2.4% when we corrected for the yaw error that the turbine was experiencing. So a summary on yaw alignment calibration, we used LiDARs using LiDARs can lead to better yaw alignment and can increase the annual energy production. The improvement will vary depending on the vane errors. So some wind turbines may have very little vane error going on, and with that, there's not much to improve on. But if there's a turbine out there that's behaving poorly, maybe it's due to vane error, and then a LiDAR can help correct that. Go back a little bit, we left off with the yaw alignment control, and now we're going to go into the second application for nacelle-based LiDAR, which is feed-forward blade pitch control. So yeah, on slide 36 here, I was talking about how we measured wind speed at one of our wind turbines at NREL. And with that, and this was without a LiDAR installed on the wind turbine. So with that, we then had the feedback from the wind turbine in red. This is showing the rotor speed of the wind turbine. And so we can see that first there's a large gust that impacted the wind turbine, and there's some delay between the wind speed that was measured and the time it impacted the wind turbine and it started to accelerate. And this is due to the fact that the mast was located upstream of the wind, and so it took some time for that gust to convect from the mast to the wind turbine. And what happened here is the gust shut down the wind turbine because the rotor speed accelerated to the point where it went into an overspeed condition and the turbine shut down. And so this is something we want to avoid when running a wind turbine. So what a LiDAR can do is provide some advanced knowledge of the gust, and the turbine can anticipate that and react to it as the gust travels through the rotor of the wind turbine. So here's a block diagram of kind of the basic feedback control on the bottom, and then we have on top in the green we have the wind, and the LiDAR is measuring the wind, and then as the wind travels to the wind turbine, the wind is going to evolve. And so we need to have some sort of wind evolution model that we apply to the LiDAR measurement, and then feed that into a feed-forward controller, which then gets added on top of the feedback controller. So the challenging part here is that the wind evolution model in reality is not going to match the actual wind evolution. So yes, as I said before, the wind is going to change between when it is measured and when it interacts with the wind turbine. So small eddies in the wind will dissipate, while large eddies will remain mostly unchanged between when the LiDAR measures it and when it impacts the wind turbine. So what we want to do is we need to design a filter that filters out the small eddies, but still keeps the large eddies there. So, and then ideally we would use an adaptive filter which would take the measurements and adapt to the changing wind as it impacts the wind turbine over time. So some results from some feed-forward blade pitch control that we've done at NREL. On the left, we're showing the power spectral density of the rotor speed, and on the right, we're showing the power spectral density of the tower 4F bending. And then in each of the subplots, we have different gains associated with the baseline feedback controller. So what we're doing here is we're detuning the baseline feedback controller, which will allow that controller to then focus on higher frequency content where we want to avoid loads. And then the lower frequency content in the controller is then taken over by the feed-forward controller. And in the blue, we have our baseline case where we're only applying feedback control to the wind turbine. And in the green, we have the LiDAR-assisted feedback and feed-forward controller. So we can see that as we lower the baseline gains, we get improved rotor speed regulation as the feed-forward controller is taking over control of the rotor speed. But then we detune it all the way down to 10%, and then we saw the rotor speed was getting less and less regulated, as we do need some of the feedback controller to control the rotor speed of the wind turbine. And then on the right half, we have the tower 4F bending, and we can see that by detuning the baseline controller, or the feedback controller, we do see a decrease in the loads experienced in the tower 4F bending. So a summary on the feed-forward blade pitch control, we use the LiDAR to measure the wind, and then we filter that measurement, and then we apply that to a feed-forward pitch controller. And so the feed-forward pitch controller can be used to regulate the rotor speed in region 3, and then the feedback controller can be tuned for loads reduction.
All right, so the next application we'll talk about is power performance measurements or power curve verification. So this is where we want to measure the wind speed and the power generated by the turbine and compare the measured power curve to the theoretical power curve from the turbine design. So power curve verification, it's required in type certification of turbines by turbine manufacturers. The process for performing power curve verification is defined in the IEC 61400-12-1 standard. And it says you want to measure the wind at about 2.5 rotor diameters upstream of the turbine using an anemometer on a met mast. So the second edition of this standard actually allows for ground-based LiDARs to be used to measure the wind, but you still need to combine that with a met mast, just a smaller met mast. And then the 61400-50-3 standard, which is being developed, will allow the use of Nacelle LiDARs for power curve verification. The expected release time is in 2021, I believe. But this standard will only allow the use of Nacelle LiDARs in flat terrain for power curve verification. So some advantages of using a Nacelle LiDAR for power curve verification. First of all, it can be more cost effective than installing a tall met mast. Since the Nacelle LiDAR will always measure the wind upstream of the turbine because it rotates with the turbine, we're always going to measure the wind that will then arrive at the turbine, whereas a fixed met mast might not measure the wind directly upstream of the turbine depending on the wind direction. And then we can more easily measure what's called the rotor equivalent wind speed with a Nacelle LiDAR. So this is a concept defined in the second edition of the -12-1 standard. And it says that the rotor equivalent wind speed is going to be the average of the cubed wind speed at different heights weighted by the relative area that those height sectors take up on the rotor plane. And then we take the cube root of that spatial average. So by combining measurements from different heights on the rotor plane, this should provide a more representative wind speed that the turbine will experience than measuring at a single point at hub height. Scanning Nacelle LiDAR can easily measure at different heights and come up with this rotor equivalent wind speed. And then for some of these reasons, such as measuring upstream and measuring the rotor equivalent wind speed, Nacelle LiDAR measurements can reduce the scatter in the power curve compared to a single cup anemometer at hub height. So that's shown in these plots on the bottom right. Some challenges with using Nacelle LiDARs for power performance measurements are that if we're required to measure the wind 2.5 rotor diameters upstream of the turbine, then, let's see, do we still have audio? Is that, all right. Great.
So
all right, so as the rotor size of turbines increases up to, around 200 meters these days, then it can be difficult to measure 2.5 rotor diameters upstream of the turbine because we can generally measure 200 to 300 meters upstream of the turbine. But if we want to measure then closer to the turbine, then we'll be measuring in the induction zone of the turbine. And this is where the velocities start to become reduced close to the rotor because of the blockage effect of the rotor. But there could be some advantages to measuring close to the rotor, such as when we're in complex terrain. Because if we're measuring 2.5 rotor diameters away, we might be seeing a different wind speed profile than what actually reaches the turbine because of the terrain effects. So we could measure closer and get a more representative wind field measurement. So there's been some projects looking at how can we measure within the induction zone and still estimate the free stream wind speed power curve verification. One project that's looked at this is the Unity project performed by the Danish Technical University. And so to do this, just like we have a wind field model that we use to estimate our wind field parameters, well, now we need to add a model of the induction zone, or how the velocities are reduced as we approach the rotor. So there's a popular, simple, one-dimensional induction zone model based on vortex theory, and it describes how the velocities are reduced approaching the turbine. It's a function of the distance, the rotor diameter, and the induction factor. The induction factor is just what fraction the wind has been reduced by when it reaches the rotor, and it depends on the power or thrust that the turbine's generating. There's a paper I'm citing here by Antoine Borrachino. It was done as part of this Unity project, where they looked at measuring the wind at different ranges upstream of the rotor using a pulsed LiDAR, and then combining these line of sight measurements at different ranges to estimate different wind field parameters. So they came up with a combined wind field induction zone model. There was a function of the hub height wind speed, the wind direction, the power law exponent for wind shear, and the induction factor. And then using some nonlinear optimization techniques, then they could find the best fit parameters based on their line of sight measurements. So real quickly, the last application area is scanning LiDAR measurements for research applications. So they can be very useful tools for doing research on turbines. One example is wake measurements. So we might want to know how the wake profile varies with atmospheric conditions downstream of the turbine. How do control actions such as yaw misalignment affect the wakes? And then we could use this information to help validate some of our engineering wake models used for wind farm design. One experiment that we did here at NREL a few years ago is measuring the wakes downstream of the GE 1.5 megawatt wind turbine at the Flatirons campus at NREL. This is using a scanning pulsed LiDAR developed by the University of Stuttgart. There was also a partner in the project. And so it measured the wind at 5 different planes downstream of the rotor. So here's some example results where this is showing the measured wake profiles at 2.35 rotor diameters downstream of the turbine for different turbulence intensity levels. And then these profiles could be compared to different engineering wake models to help validate and tune those models. Then another part of this experiment was to intentionally misalign the yaw position of the turbine with the wind direction, because this is can be used as part of wake steering control, a type of wind farm control where you want to apply a yaw misalignment to deflect the wake away from a downstream turbine to increase overall power production. So on the top row, we have the wake profiles measured by the LiDAR for baseline yaw control for different wind speeds. And then on the bottom row, the wake profiles are measured for a 25-degree yaw misalignment. So we can measure how much the wake was deflected with the yaw misalignment and use that to compare to some of our engineering models.
Okay, so on to a summary of part 2. First, we talked about the yaw alignment calibration application of a nacelle-based LiDAR, and we showed that LiDARs can be used to improve the yaw alignment of wind turbines, and this can lead to an increase in the annual energy production. From that, we then talked about feed-forward blade pitch control and how LiDARs can be used to anticipate the wind disturbance and reduce turbine loads that turbines would otherwise experience.
All right, and so we saw how nacelle LiDARs can improve power performance measurements. They can reduce scatter in the power curve and can allow us to measure in the induction zone. And then scanning LiDAR measurements can be used for research purposes. We just looked at how they can be used to measure wakes behind a wind turbine rotor. So yeah, thanks for your attention. And
thank you very much.
Thank you, Eric and Andy. That's a great presentation. And sorry for that minor disturbances, and we'll see how much of that we can recover. And now I would like to open this session for any question answers. And please unmute your mic and ask questions directly to our presenters. And probably 5 minutes, okay? Okay. Yeah, we'll stay here for 5 minutes for your question, please. Is there any question?
Yeah, so I see one question on the chat, and that's the question is can we just install the LiDAR on the ground and measure the wind speed at the installation site? So yeah, that's one topic that we didn't cover is ground-based nacelle or ground-based LiDARs, and there are applications for that as well. For the feed-forward blade pitch control, I would say it would be very difficult to have a LiDAR on the ground because you want it pointing into the wind direction ahead of the wind turbine at all times.
Yeah, and so we could use a ground-based LiDAR to measure the wind at the installation site, you know, for a resource assessment. But I don't think we could use that directly for the power curve verification. But it could be used to help calibrate, or you know, determine the correction needed if we're going to be measuring the wind at a different location in complex terrain. Yeah. So then we have another question comparing pulse and continuous wave LiDAR. Does one type work better in low aerosols if measurements are taken at multiple distances from the LiDAR?
So yeah, I would say that with low aerosols, the continuous wave has the advantage that it's focused, and so you're going to be focusing more of that beam energy into one area, and so you're then going to get more of a return in that smaller area, despite the low aerosols. And then with the pulse LiDAR, what you would want to do is pump more energy out into the atmosphere, so have greater pulse energy. And the limit there is then eye safety for people that will be in the area. As you put more energy into the laser pulse, it's going to get to the point where it's not eye safe anymore, and so there's limitations there because we don't want to be injuring people's eyesight. I don't know if you have anything else to add.
No, I don't think so. Just, yeah, I think continuous wave LiDARs, you know, as you measure further away, you're also measuring over a larger volume, so that helps correct for some of the signal loss to help give you more carrier to noise ratio at the greater distances. So another question, what software do you use to interpret the data from the LiDAR, and how much post-processing is required for the raw data from the sensor? A lot of the commercial LiDARs will just directly report their reconstructed wind field parameters, like the wind direction and wind shear. So you don't really have to do much post-processing yourself for nacelle LiDARs, but there's always the option to use the raw line of sight velocities, and you can write your own program to use your own wind field model to reconstruct the wind field.
Yeah, so the next question that I see is, can nacelle-based LiDAR be used to support smarter dynamic yaw alignment and adjustments? And my answer to that would be yes, it probably could. It's something that we have not looked at. So yeah, things I could think of is maybe instead of having a static system where you wait a certain amount of time for a yaw error to accumulate, you could maybe adjust that with measurements from the LiDAR for changing atmospheric conditions.
Yeah, that's right. And maybe one thing I would add to that is, because of this Cyclops dilemma, if there's some horizontal shear, we might misinterpret that as a yaw misalignment. So we have to be careful that we don't overreact to small changes in our measured yaw misalignment, because it could be due to turbulence across the rotor. So if we average over enough time, then we could use those measurements for yaw. All right. So is that okay? So I think we have to wrap it up now. But yeah, thanks for the questions.
And apologies for the technical issues.
Yeah, thanks for bearing with us.
I can see that some question in the chat room, and we'll write those questions and send it to our presenters, and we'll get back to you. And sorry for we are running a little over the time, and we have to stop here. And within 2 weeks, probably this webinar will be available in NREL Learning channel, and we'll update you with the link. Thank you very much, and we are going to stop here. Thank you.
Thank you.
Bye-bye.